Good evening, everybody. We were talking about that analytical methods which are utilizing some electrode potentials, and we basically considered these as the electroanalytical methods. So, when we consider that some electrode potential or the current or the voltage can be a measurable quantity for your analysis, then we get the corresponding electroanalytical method. So, this study basically includes when you have the analytes and we will be able to measure the corresponding potential and or current. So, potential in volts and the current in amperes in any electrochemical cell containing the analyte. So, it is a very simple technique what we can consider that the different types of titrations what we are looking from our all earlier classes, that titrations what we know that the corresponding neutralization reactions between H plus and HO minus, that means hydrochloric acid and the corresponding base as the sodium hydroxide. So, when we get this particular neutralization reaction, what we try to monitor from there is that we basically add some indicator, and that indicator will change its two colors. One is in the acidic form and the other will be in the basic form. And when we know that it passes through some pH value, so this is the typical plot where one axis will be utilizing for the volume of the titrant, that means if we add the corresponding acid or the base, and another is that particular parameter. So, when we consider the neutralization reaction in terms of the neutralization of the acid or the base or any carbonate or the bicarbonate salt, what we see that this particular one is the pH, that means the corresponding hydrogen ion concentration, and that hydrogen ion concentration we can monitor. So, there should be some pH change and we can locate the corresponding endpoint by using that particular solution, few drops of those indicators which can change from one color to the other, that means we are passing through this particular color change range for the corresponding indicator. So, this particular parameter basically is dependent on the corresponding concentration of the hydrogen ion and its neutralization. So, when we consider that any other sort of titration and we will utilize the corresponding electrode potential, say, or the current we can use. So, this we will see that how we can correlate this particular parameter, this pH, to some electrode potential which is your millivolt. So, the voltage we can measure. So, this corresponding electrochemical cell, if we have, and within that electrochemical cell, if we take the analyte in it and the same burette basically. So, this is the typical burette pipette reaction, what we know that this is giving you that corresponding dropwise addition of the hydrogen ion. So, within the electrochemical cell, so the sensing points, that means the sensing points is your electrodes. So, those electrodes are available, and if we can externally measure the corresponding current which is passing or the voltage between these two electrodes, that is why we are discussing about the corresponding electrochemical cell as well as the galvanic cell. So, what amount of that potential can be developed by inserting these two electrodes such that we can monitor the corresponding change in the analyte concentration. So, we will be monitoring because something we are adding and some sort of this neutralization reaction is happening, and we will try to monitor the corresponding millivolt. Say how you measure that is the corresponding potential we can measure. So, that is once we measure this potential, we will get a technique which can be termed as the potentiometry. So, we all know that the potentiometer, what is potentiometer? So, this will be immediately termed as the corresponding potentiometric titrations. And since we have the pH, and here without using any instrument or anything or any meter for your analysis, this is the corresponding color change. So, visually we detect the end point, and sometime this particular detection, if we have a very low concentration which we cannot detect through our eyes, so we can take the help of the corresponding spectrophotometer that we have seen, that how we can use the spectrophotometer for the different spectrochemical analysis. Now, if we consider that how we measure the pH values, because we should know that this measurement of these pH values, we all know that there is a one small benchtop type of instrument is available to everybody and is nowadays is available to everywhere. So, is your pH meter. So, this pH meter, we have something, that means we will find that a electrochemical cell arrangement will be utilized to detect something which is your the corresponding millivolt values, and these millivolt values can be correlated to their pH. So, what we were earlier studying is a very interesting one, that we just plot this as the pH and the corresponding volume of the analyte. So, it is not voltage, do not make any mistake over here, that is the volume of the titrant. Okay. So, if we get that particular millivolt, so if the pH meter is available to measure the pH, and if one of the parameter is by measuring the corresponding voltage of the cell, the electrochemical cell. So, instead of plotting these pH values, we can plot these millivolt values over there. And what will happen if we want to see the change in these millivolt values? So, if this is the axis, whether we will get this sort of plot or the other sort of plot, where we can clearly detect the corresponding end point. We can pinpoint this particular range at the middle of this thing, that means it is not changing much from this volume to this volume. So, if we can find that this sudden change in these millivolt values are also there. So, like that of our titrametric method using indicator and the burette pipette titration, the manual titration what we can have, can also be utilized for your potentiometric estimation or the potentiometric titration. So, this gives rise to our one of the most important electrochemical methods, where we can use the potential to measure the corresponding endpoint or detect the endpoint. So, this is the first thing what we will be seeing here, that is why the measuring of potential. So, in volts or in millivolts, and at the same time also we will find that in some other methods, that once we measure the potential, we should also be able to measure the corresponding current in any electrochemical cell containing the analyte. So, that is the very most important thing of our concern, is that you must have the electrochemical cell, and that particular electrochemical cell will have the corresponding analyte. That means, if you have the unknown base in your electrochemical cell, so instead of using the typical conical flux what we use for your titration, the acid base titration, now is that you must have something, that means you have the electrochemical cell, and we all know that is not a very complicated situation of making electrochemical cell, because if you have something, because in our previous class we have seen that when you are dipping a iron nail in a copper sulphate solution, that gives rise to a corresponding cell of your deposition of copper on the iron electrode. So, you have something that is the half cell. So, if you just simply complete that for 2 half cells, and you can do the same reaction within a burette. That means, your container is nothing, because earlier we are going for these titrations, say using a conical flux. So, you have the conical flux over there. Now, this electrochemical cell, the concept of getting a corresponding electrochemical cell, it should have a wide mouth thing. That means, the simple beaker, how you can use that thing, say of 100 milliliter capacity, and you have the corresponding analytes in it. So, already taken the measured volume of this, what you are there in this conical flux also for your titration. So, then you just this particular part, that means what is your electrochemical cell. So, this is your electrochemical cell. You have to insert the electrode, the cathode as well as the anode, and you just add the corresponding analyte. That means, this burette will come over here. So, this burette will be there, and drop by drop addition of that particular titrant will change the corresponding reaction medium. That means, it will go from a one particular basic side to the acidic side, and during that process you have a corresponding or continuous change in the corresponding millivolt values, and we will try to measure, because this has a digital reader. That means, the display unit of this pH meter will record the corresponding values of your millivolts. So, what we see for these analytical methods utilizing the electricity. So, definitely we will get three main categories. So, what are those main categories that we should know very nicely? The first one so far we are discussing here now is that your potentiometry, like that of your potentiometric titrations. So, what we measure there? We measure the difference in electrode potentials between the two electrodes there. So, is a very useful and the most simplest technique, that the measurement of the electrode potential by using two electrodes inserted within a cell, and that is your electrochemical cell. Now, if we try to measure the corresponding current, the cell's current is measured over time. That means, how much charge, basically not typically the current, it is the charge, what amount of charge in terms of coulombs what we can pass. So, that the coulometry is the passing of the electrical charge through that particular solution, and something is happening, and we all know that when we use that particular charge to a system, either the charge you take out, the electronic charge we take out, or the detachment of the electrons from the system is your oxidation, or the addition of the electrons to the system, that means the reduction. So, this particular system should give you a corresponding oxidation as well as reduction. And the third category is your voltammetry. So, is a different type of thing, that means you have the cell's current is measured while actively altering the cell's potential. That means, you have voltage, the volt, and the ampere. So, the voltage as well as ampere will now measure. So, at certain point you have a huge change of the corresponding current which is passing through that particular point, and we get some informations not only regarding the finding out the unknown analyte concentration, but the nature of the corresponding active species. That means, whether you have a oxidizing species or a reducing species, and the electrodes are responsible for your oxidation and reduction of that particular species. We can monitor for a voltammetric measurements that we will see, and this also give rise to the corresponding birth of the voltammetric sensors. You can sense that thing. That means, some analyte concentration which is unknown. So, unknown analyte concentrations we can monitor using this particular voltammetric technique. So, the first one we will be just discussing over now is your potentiometric. So, how you do the potentiometric titrations. So, first thing what we can see is that how you get the corresponding potentiometric titration curves. So, it is a very useful technique for determining the alkalinity of sea water, because we know that the sea water is alkaline. How much alkalinity you have, that means, if you have a very low concentration, not all the time you can go for your corresponding conventional or manual acid base titration using some indicator, but your potentiometric titrations are very much useful to determine the corresponding alkalinity of the sea water, how much alkaline salts are available in your sea water, like that of your sodium carbonate or potassium carbonate or sodium bicarbonate or potassium carbonate in those sea water. So, this potentiometric method of analysis is based on the measuring of the potential of the electrochemical cell without drawing appreciable current, which is very important, that the cell is not meant for drawing the current, but still we will be using some electrochemical cell such that we can monitor the corresponding change in concentration, the change in the corresponding concentration of say one species, which can be your the corresponding ferrous ion concentration and any other oxidizing agent. So, large number of industrial places or some other applications for our life processes or the analytical chemistry which we apply for analyzing the blood or the urine or any other fluids what is available from our body, that means the corresponding clinical chemistry. So, the clinical analytical chemistries also will be relying on this simple pH meter what we are discussing now. So, anything related to your pH, that means your consumer products, your creams, the face creams we use, the soaps and all whatever we consume as our daily needs. So, that can be utilized for your pH determination. Then clinical laboratories basically determine not only the pH of the blood, but also the dissolved gases, because the dissolved gas like that of your carbon dioxide is more. So, how we can monitor the corresponding concentration of carbon dioxide by using this technique. Then what we just drain out the industrial and municipal effluents. So, the bases or the acids, whether these are the effluents, because we know depending upon the industrial activity what we can have, either you discharge into some drain water or ultimately to the river water or to the sea water, that a solution which is your municipal effluent, and that municipal effluent can have either acidic nature or a basic nature. So, direct monitoring by inserting those electrodes, considering that the container which is taking your effluent, you can go for the potentiometric estimation for determination of your pH and the amount of the corresponding species which is responsible for giving you that pH of your municipal effluent. So, very first thing what we do and what we determine is that the determination of the pH of anything, starting from your any other solution, the water we drink, the blood we have or the municipal effluent we can have. And it also give another advantage to us, that continuously we can determine that particular pH, and once we determine that particular pH and what we are throwing away, what we are discharging in the river bed or the sea bed is the corresponding concentration of the pollutants which are responsible for giving you the required amount of the acids or the bases, that means the acidic substances or your basic substances, to give you the corresponding pH of that particular solution. And people who are dealing with the oceanic activity, that means oceanographers, they basically determine the corresponding amount of carbon dioxide and other related variables which is dissolved in the sea water. So, how much your sea water is contaminated, that basically can be determined by this particular type of titration which we consider as your potentiometric titrations. So, it is a very simple one, as I told you, and is also inexpensive, and it includes a reference electrode, a indicator electrode and a potential measuring device. So, as we have seen our previous class, that we use the corresponding electrochemical cell. So, in this particular electrochemical cell, we have something for that potentiometric method. So, we have a reference electrode. So, this reference electrode, what we have seen, this reference electrode, as we have seen, we are discussing, for that is also for your silver chloride or silver ion silver electrode, or simple saturated calomel electrode, or standard hydrogen electrode. So, we determine this particular half cell potential by attaching these to standard hydrogen electrode, and with respect to the standard hydrogen electrode, we found the corresponding potential of this. So, this can behave as a corresponding reference electrode for your measurement, and another will be your indicated electrode. So, which is your, we can consider this as for in other measurements as the working electrode, but this is your indicated electrode. So, combination of these two, that means we have two electrodes. So, what are these corresponding available potentials? So, you have to measure the corresponding potential out of this thing and this one. So, a potential measuring thing, that means a reader is available. So, that reader will record the corresponding potential between these two, and that can be reported with respect to the corresponding silver ion electrode or the silver chloride electrode or saturated calomel electrode. So, you have to measure the corresponding potential between these two electrodes. So, what we get over there is that a simple system that where you have a digital meter, and this particular digital meter what we are talking about, that you can consider that what we see digitally, that means it has a typical display unit, and display unit, say what is shown over here is typically your 84.2 millivolt. That means in the range of simple millivolt you have it, and you have taken a open beaker as I told you just now, and you have the analyte. Only thing is not there, that is not the complete arrangement for your potentiometric titration for recording some neutralization reaction or some precipitation reaction or some redox reaction. So, you can monitor all these together utilizing this particular technique. So, as I just now told you, that is the corresponding figure for is what we have taken from any book, that is the Skoog's book, that you have the reference electrode. So, is the E ref. So, E ref value is there, and you simply insert something, your metallic indicated electrode, it can be a platinum wire only, or it can be some plate, the metallic plate. So, that will give you the corresponding potential as your E indicator. But within this particular reference electrode, you have some porous membrane at the bottom, this round point, that is you have the porous membrane and the salt bridge, because this indicator is directly inserted within the analyte solution, but this you see is glass cased. So, casing is from the glass, and you can have some porous membrane such that you can get the corresponding exchange of the solution concentration such that the electrode is exposed to the corresponding concentration of your analyte, and is not that the analyte will go inside and contaminate this thing, but its selectivity. That means, the membrane what you have, we all know that the membrane is not that is a typical thing that is just control the corresponding passage of the ions, and we get somewhere that is ion selected. So, if we talk in terms of the corresponding thing, that you measure the corresponding potential in terms of your millivolt values in the pH meter and the corresponding proton concentration, the corresponding proton what is going or what is exposed for this. So, the proton concentration is moved through this porous membrane. So, we can detect the change in the corresponding proton concentration by measuring the potential where you have the corresponding E cell. That means, it is the complete cell, and these are the two half cell values. That means, we all know that the potential for the corresponding indicator electrode, we call it as the electrode right. So, the right sided electrode minus the corresponding left sided electrode, that is the usual convention what we use to calculate out the corresponding potential. That means, the total potential for the cell plus some correcting value we use, that you can have some junction, as we have seen that some inverted U tube we have seen earlier, that inverted U tube we use to get that cell. So, this is the corresponding value for your junction, it is the junction potential. So, once we add up all these three together, you get the corresponding cell potential values, and when the cell potential values will be changing, that particular display will record that thing, and we will get that thing also for your measurement, that as an indicated electrode has a potential that varies in a known way by variations in the concentrations of the analyte. So, what is your analyte now? that you now get all these informations that you have a pH meter or a digital meter you have. So, we are not calling it as a pH meter right now, but if it can sense the corresponding concentration of the hydrogen ion, what we will see here is that when the concentration of that hydrogen ion is changing, that will directly saying as is your analyte. Because analyte, the corresponding term for your analyte, what we will be looking for your analysis is the generalized term what can be applied to your proton, what can be applied to your corresponding something which is your reductant, that we can determine that reducing agent like your ferrous ion. If we want to determine the concentration of unknown ferrous ion, what will you do? You will try to react it with some oxidizing agent like your permanganate or dichromate or the steric ion concentration, and you go for electron transfer reactions. But here how the proton is going for your electron transfer reaction. So, that is the very basic simple thing is that we will have some proton concentration. So, the change in proton concentration will be sensed in terms of the charge transfer, in terms of the electron transfer. So, this is particularly the figure, and this thing is very detail is available in your book, the fundamentals of your analytical chemistry, written by Skoog and West. So, the reference electrode, the first thing, the first component what we use your reference electrode. So, as we discussed earlier, once again we just recall back that saturated calomel electrode, the SCE. The calomel electrodes are consisting of a mercury in contact with a solution that is saturated with mercurous chloride, and the corresponding name of this, the traditional name, or you can consider it as the corresponding trade name without knowing the formula, as chemists write as Hg2Cl2, we can say that it is calomel, and also contains a known concentration of KCl. So, Hg2Cl2 in presence of KCl will give rise to the calomel electrode where you have the mercury in contact with that. So, the arrangement for that is little bit complicated, where we see that you now have a H type of tube. These are two caps basically. So, when you get this H type of tube and you have a long end of 6.5 centimeter type of thing, and you have a separation of 2 centimeter, and you have a 6 millimeter width for that, and is the Weicker plug, which is your typical permeable membrane, because this permeable membrane which is made up of some Weicker is also a trade name for some material, some polymeric material which can only pass you some selective ions like your protons. So, is ion selective get what we get. So, ion selective membrane we get, we can consider this as the ion selective membrane, and your reference electrode is there. What we have defined over here is the presence of KCl solution, then KCl crystals, because it will be within the saturated one. As we discussed in case of silver chloride silver electrode, that you have the saturated solutions of that, because that concentration will not change. So, if you have a calomel paste, this is your calomel paste, little bit darker, and you have the mercury at the bottom, and this particular one you have, and you have some wire fixed over it, that you just mercury is connected to some platinum wire, that means it gives rise to the corresponding electrical connection for that thing. So, the designing of this electrode what we can have, and that basically we know now how to write the half cell. The half cell is nothing but your this mercury, then you have the calomel, and which is there in a saturated KCl solution of some concentration, x molar of that KCl solution. So, the x molar of that KCl solution with this will give rise to the corresponding values for this reference electrode, because the reference electrode is nothing but a half cell, and that half cell will have some potential value, and which is dependent on the corresponding concentration of your potassium chloride. So, we measure that, we find that, and we then try to correlate with that of your indicator electrode. So, when you have the indicator electrode, so is like that of your calomel electrode, you can have the silver chloride electrode, where we can should be able to write down in form of that corresponding saturation of the silver chloride and the corresponding KCl saturated solution and the electrode reaction. What we knew earlier in our previous class, we discussed it in detail, that how you go for the reduction of silver ion to silver in presence of that silver chloride. So, that potential we get, that 0.244 volt we get, and for a saturated silver chloride electrode we get is 0.199 volt. So, the calomel and the silver electrodes, you have the different values of all these things, and we can use this where you have the coated silverware and layer of silver chloride it has, and it is dipped in the KCl solution and the saturated solution of silver chloride. So, what we see next, that how we can utilize these half cells and the reference electrode and the indicator electrode for your titrations, which we can consider as your potentiometric titrations, that we will see in our next class. Okay, thank you very much.